All right, everybody, good morning. Welcome back. I hope everybody had a great weekend. So we started on Friday talking about the elements of symmetry, beginnings of our discussion on symmetry, chapter 4. We talked about symmetry elements and symmetry operations, and we built up the full list of symmetry operations for a non-molecular example, in that case a snowflake, right, which had six-fold symmetry. What we want to do today is start by using a molecular example, and then we're going to jump into our discussion of point groups. So point groups are basically the complete set of symmetry operations that describe a given molecule or object. Okay? So all molecules have and fall into one of a variety of different kinds of point groups. And what we want to try to understand is how we can assign point groups to different molecules based on their symmetry operations, the symmetry operations that they possess. Okay? So let's get started here. Our example is going to be staggered ethane, which is a nice example because we have several different symmetry operations that this molecule possesses. So this is just standard notation, right? If we just have a normal line, it's in the plane. If we have a solid wedge, it's coming out of the plane of the board. And if we have a dashed wedge, that atom is going into the plane of the board slightly. Okay, so this is just like organic chemistry. What we want to do here is identify, first of all, what its highest order rotational axis is. This is often the easiest place to start in understanding the different symmetry operations of a molecule. And so we can paint the molecule this direction, where we're looking perpendicular to the CC bond, or we can look at it along the edge here, so down the length of the CC bond, looking from the left-hand side. Okay? And we can assign A, B, C, D, etc. to all the different hydrogens. What we're going to see is if especially we look at it in this particular orientation here, it becomes fairly obvious that there's a C3 axis to this molecule. If we rotate by 120 degrees in a counterclockwise sense, then we're going to generate an equivalent configuration of that molecule, right, where we can't really tell that it's been changed at all. And all we've done is we're going to cycle the labels of the hydrogens. So HA is going to go to HC, HB is going to go to HA when we perform the C3 operation. And after we perform the C3 operation, we have an equivalent configuration that looks like this. Okay? Because we have a C3 axis in this molecule, we can perform the rotation twice. We can do a 240-degree rotation. That would be our second C3 operation. That would drive HB to HA and so forth. So these are the three hydrogens coming out of the plane of the board. And then these are the three hydrogens that would be going into the plane of the board. Okay? And you can see after the second C2 operation, or the second C3 operation, excuse me, that we still have an equivalent configuration. We have a good symmetry operation for this molecule. If we do it a third time, do the C3 a third time, we recover the identical configuration that we started with. In other words, we perform the operation E. Right? So C3 cubed is equal to E. And we can play other games. We can do a C3 squared directly and get this configuration. So these particular operations, the C3 related operations, are good operations for this particular staggered ethane molecule. And so we would say that so far we can say that we have the E operation, of course. We have a C3 and we have a C3 squared. Those are the unique operations that come out of the C3 axis. Okay. What other symmetry elements and operations pertain to this molecule? Well, we can tell right away that there's going to be several more, at least. Okay. So let's look first at other axes along this same axis here. Is there a C2 axis along that axis? Is there a C4? Is there a C6? What do people think? Do we see other rotation axes along that direction? We'll get to the S's in a bit. What about just proper rotations? Any other proper rotations? Is there a C2 along that direction? So if there were a C2, what would happen? HA would rotate 180 degrees down. It would be pointed directly in the plane of the board here. That would not be the same configuration, right? So there is no C2 axis. There's no C4 axis. There's no C5. The only thing this thing has is a C3 axis in that direction. Okay? What about other axes, rotational axes, perpendicular to this C3? So if you look at the molecule and look perpendicular to the principal axis, we actually have three perpendicular C2 axes in this molecule. Remember that point groups or objects here are going to have either 0 or n perpendicular C2 axes. In this particular example, we have 3 perpendicular C2 axes, each one of which is perpendicular to a plane that's defined by 2 of the hydrogens and the 2 carbons. So here's an axis coming out of the board that's a C2. If we rotate 180 degrees around this axis, HA goes to HF, right? HB goes to HE, and HC goes to HD. So that is a good symmetry operation, a C2 perpendicular to this plane right here. There are 2 more that are perpendicular to the other planes that contain the hydrogens, and those are inscribed here in this axis view of the molecule. So we have our C2 here, we have another C2 that's perpendicular to this plane, and we have a third C2 that's perpendicular to this plane. Okay. C2 rotation around any of those axes is going to give you equivalent configurations that look like this. We can describe these different C2s by differentiating them with primes. So we can just call one arbitrarily the C2, one a C2 prime, and one a C2 double prime, just to tell that they're different axes. It's just a totally arbitrary designation. But the basic point here is that in addition to our C3 axis and the operations that pertain to it, we have 3 additional operations, C2 operations perpendicular to that C3 axis. There are 3 of these perpendicular C2 axes. Yeah, Jeffrey?
Sorry, why do we add the primes again?
The primes are just to differentiate the exact axis we're talking about. So if we wanted to describe this one, we could just call it C2. But to tell that we had another C2 axis that's different from this original axis, we'd give it some other designation. And the convention is just to call it a prime, or double prime, or triple prime, or whatever. We could describe it any way we wanted to, right? But we have to use some kind of differentiation. Okay. So now we have 6 symmetry operations that we've built up for staggered ethane. Right? We have the C3 and its variations, and we have these perpendicular C2s. That describes all of the proper rotations for this molecule. Okay? We can't find any additional proper rotations. Let's move on to reflections, okay, as the next symmetry operation that we care about. What reflection planes are there, mirror planes in the molecule? Well, there are 3 mirror planes that are just like the C2 axes, perpendicular to those C2 axes. So there's one mirror plane in this plane. And you can see here that if you reflect across this plane, HA and HF stay where they are, the carbons stay where they are. But HB and HC are interrelated, and HD and HE are interrelated. This plane here is this plane that I've drawn right here. If we do the reflection operation, you can see that HA and HF stay the same, but HE and HD change, HB and HC change. But we generate an equivalent configuration. The molecule is unchanged except for our imaginary labels on the atoms. Okay? Remember that these labels are imaginary, right? They're just there to help us bookkeep and tell what's going on when we do the operation. Of course, they don't exist in reality. In addition to this mirror plane, there are mirror planes in that plane and also in this plane. Right? The other planes that contain the carbon atoms and 2 of the other hydrogen atoms. And if we perform the mirror operation, you can see that you get equivalent configurations. Okay? So we've added to our 6 proper rotations, we've added 3 more symmetry operations that correspond to the mirrors, right, to the mirror reflections. One thing that's important to note, or to ask ourselves, I guess, is there a sigma H, a horizontal mirror plane in this molecule? The horizontal mirror plane, remember, is the one that's perpendicular to the principal axis. And so that would have to be a plane that cuts right here, perpendicular to the principal axis, which is this axis, the C3 axis. So is there a mirror plane here? And the answer is no, right? Because if you reflect through the plane, HA would go over here, and there's no atom there. Okay? So sigma H is not a symmetry operation of this molecule. So we have 9 so far. Okay? Are there any more? There are more. The inversion operation is a symmetry operation of this molecule. The inversion, remember, you take coordinates x, y, z, and you change them to coordinates negative x, negative y, negative z, through some center of the molecule. The center of the molecule, the inversion center in this particular case, is at the center of the carbon-carbon bond, right in the midpoint. If we perform the inversion operation looking at the molecule in this orientation, you can see that you're going to take HA through the center. It's going to pop off at HF. And so will HF go to HA, and so we have swapped them here. And the same thing for HB and HD. This is above the plane, that's below the plane. So it passes through the center and goes below the plane. And the same for HE and HC. Right? And the carbons, of course, are also going to be interrelated by an inversion operation. So we generate an equivalent configuration. We can see it perhaps more easily if we look end-on the molecule. Right? That takes the 3 hydrogens that are popping out of the board, right, and swaps them with their respective partners in the board. And so we have an inversion operation as well. That's so far 10 total operations that we've tallied up. We can only have 0 or 1 inversion, and so we found that we have 1, so the game's over for inversion. And we've looked at proper rotations, we've looked at reflections, and we've looked at inversion. The last symmetry operation class is the improper rotations. So let's look and see if we have any improper rotations. And Glenn alluded that we probably do have an improper rotation, or 2. And the improper rotations in this case are parallel with the C3 principal axis, and they are the S6 improper rotations. So remember what S6 means. Well, first of all, let's remember what an improper rotation is, right? Improper rotation is a rotation followed by a reflection perpendicular to the rotational axis. Okay? And S6 means that we do a C6 and then we do a perpendicular reflection. And you can probably see right away how an S6 operation is going to be a good operation for this molecule. Let's look end-on to describe how this is going to work out and prove to ourselves that it generates an equivalent configuration. So here's the original molecule before the operation. Just end on there. Let's perform our C6. That's a 60-degree counterclockwise rotation. Okay? So that sticks HB here, right? 60 degrees. It goes like that. HE goes to there, 60 degrees, rotation, and so forth. Okay? Notice that a C6 does not generate an equivalent configuration. Right? This is not the same as this because these atoms here are pointed out at us and they were pointed in the same orientation before. So C6 is not cool, but an S6 is because after we do our C6 operation, we perform our perpendicular reflection. That pops HA, B, and C into the plane and brings D, E, and F out of the plane. It gives us this orientation after that perpendicular reflection. And this orientation here is an equivalent configuration to this guy. Okay? So the C6 is not a good operation, but the S6 is a good operation. And just like the principal axis, we can continue to do S6 operations. And what we're interested in is what S6s are unique, okay, that haven't already been described in another form. If we perform a second S6, then we rotate 120 degrees and we do a mirror reflection once and then twice. That's the same exact thing as just doing a C3 operation. Okay, so we could describe it as an S6 squared, but we've already seen that that's a C3. We've already accounted for that particular operation in our list. Okay? So that's not a unique one. And in fact, there aren't that many unique S6 operations that haven't already been described in other terminology. Here's all the possible ones, right? S6, 2, 3, 4, 5, 6 times. If you do it 7 times, it's the same as doing it 1 time. So we only have to account for 6 of them. Right? Well, an S6 by itself is unique. Okay? There's no other operation that we've previously described that will accommodate or will achieve that same operation, right? 60 degrees and then a reflection. But doing it twice is the same as C3. Doing it 3 times, right, is just an S2, and we've already said that an S2 is the same thing as inversion. Inversion can be understood by doing a 180-degree rotation and a reflection. That gives you the same exact result as doing the inversion in a so-called single step, right, bringing everything through the origin. Okay? So the cube is not original. What if you do it 4 times? Well, that's the same thing as doing a C3 twice. If you do it 5 times, that's a unique operation. Okay? We haven't previously described one that's going to do that. Okay? We do 300-degree rotation, and then we reflect, 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 reflect. Okay? That's a unique result. And if we do it 6 times, that's just identity. We already know that. And so the unique additions to our list are just 2, right? Of the 6 S6s, only doing it once and doing it 5 times gives us a unique new operation that we need to add to our list. Okay? And so now we've gone through all of the symmetry operations and we've tallied them all up. What are we left with here? This is our final table for staggered ethane. Keep in mind that staggered ethane is going to be different than eclipsed ethane or other conformations of ethane, right? Because you can imagine if you rotate along that carbon-carbon bond, you're going to change the symmetry of the molecule. Right? Well, here's our tally. We have an identity operation. There's always one for every object. We have 5 individual rotations. 2 of those are C3s, right? The individual C3 and doing it twice. And the other 3 are the perpendicular C2 axes that we described. Okay, so that's 5 total proper rotations that are independent. We have 3 reflections. These are the so-called dihedral reflections. Okay. These are parallel with the C3 axis. We have an inversion. That's 10. And then we have 2 improper rotations giving us 12 total symmetry operations for this particular molecule in this conformation. This set of 12 is a unique and complete set of operations that describe all the symmetry properties of this molecule. Okay? So these 12 symmetry operations describe completely and without redundancy the symmetry properties of any object that looks like staggered ethane, right, in a mathematical sense. The complete set of symmetry operations for a molecule or an object, we call this the point group of the molecule or the object. And we'll describe how we can categorize point groups in a little bit. Just to give a prelude here, the point group of staggered ethane is so-called D3D. Okay? We would say it has D3D symmetry, or it belongs to the D3D point group. Okay? That's what we would say about staggered ethane. If we know that it's a D3D object, then we can use that information extraordinarily powerfully to understand things like molecular vibrations, the molecular orbital construction for the molecule, et cetera, et cetera. And that's kind of what we're going to be doing over the next few chapters. Okay? It's taking this information and what we know about that particular point group and making use of that to simplify calculations and to give an intuitive picture of what it should have in terms of the number of molecular vibrations, et cetera. Okay? It's actually quite beautiful how this all works out, as you'll see. The total number of operations in any point group is called the order of the point group. We just add up all the operations. So the order of the D3D is 12. Okay? The symbol for order is usually baby h, okay, little h. And we'll use this quite a lot later. So just remember that the order is simply the number of symmetry operations in the point group. The order is always an integer multiple of n, the principal axis n. So in this case, the principal axis is the C3 axis, right? It's the largest value of n in the point group. And so we have 12 operations. In this particular case, the multiple is 4, and so the order is equal to 4 times 3, or 12. Okay? It's not always equal to 4 times n, but it's always equal to an integer times n. Okay? All right. Are there any questions about this so far? So this is our first real molecular example. We have shown actually a fairly complicated point group as far as it goes, because there's 12 operations. That's a fairly reasonable number of operations. What we want to do now is lay out the landscape for what all point groups look like, okay? Categorize the point groups, and describe a procedure by which we can assign point groups rapidly. So we don't want to have to, and you won't end up needing to, go through all of the different operations in order to assign the point group. Pretty soon you'll be able to assign point groups very rapidly. Okay, within 10 seconds, let's hope. That's kind of the goal, I would say. Okay? So we're going to take this procedure that took us 20 minutes or whatever, and we're going to narrow it down to 10 seconds. Okay? How are we going to do that? Let me first summarize. This was supposed to be the end of the first lecture here, but I was a little slower than I expected. So let me summarize what we know about symmetry, elements, and operations. Elements are geometric entities, right? Planes, lines, and points. The operations are movements with respect to these geometric entities. Okay? And what we're going to do is we are interested in movements between equivalent configurations. When we close our eyes, we do the operation, we open our eyes, we can't tell the operation has been done. That's what the equivalent configuration means. In other words, indistinguishable from the original configuration. However, there's a discrimination here. Indistinguishable is not the same as identical. If we have our little labels on our atoms, like for staggered ethane, there were lots of equivalent configurations that were indistinguishable if we took the labels away, right, the imaginary labels. But an identical configuration is one in which the labels are in exactly the same place as well, right? So if we perform the identity operation, we have identical configurations. Right? So there's a slight distinction there that sometimes is important. Equivalent or indistinguishable, not necessarily identical. We're describing molecules in terms of their point symmetry. What does point symmetry mean? It means that at least one point in the molecule remains stationary when we do the operation. Okay? And you'll notice that all of the operations that we've described, that's true. Right? Inversion, there's a point that remains unchanged. Rotation, there's an axis. Right? Reflection, there's a plane. So we're not interested in molecules translating through space right now. We're just talking about the object in some sort of mathematical vacuum, and we're doing point operations to it. And we've shown that there are many different ways to describe the same sort of operation. When that's true, we always try to use the simpler description. Okay? So in case of having an S6 squared, we know that's the same as a C3. In all of the tables and so forth that we'll see, it's always listed as a C3, not an S6 squared, just to keep it as simple as possible. That's the convention. Okay. Let's now move into point groups and how we can order, classify, and determine these different point groups. Okay, we start with the simplest point groups. These are the low symmetry point groups. Okay. These point groups have only one or two symmetry operations. Okay. The point group labels in the following slides are going to be in these red numerals here. So point group, we call this the C1 point group, the CS point group, and the CI point group. These are the three simplest, lowest symmetry point groups. Directly below the point group in red is this curly bracket notation. This means the complete set. So this is mathematical, right? Complete set of operations contained in this point group. That's what I'm trying to say here. And so in the C1 point group, you see that the only operation that the C1 point group objects have is the identity. That's the complete set. This is the lowest possible symmetry. In other words, we'd say this has no symmetry at all. It's asymmetric. A molecule that shows that possesses the C1 point group or is in the C1 point group is this particular methane-like molecule. You can see that there's no rotational axes of any sort. There's no C3 axis. There's no C2 axes. There's no mirror planes. There's no inversion center. There's nothing. Okay. Highly asymmetric molecule. An object from everyday life that has got the same point group is a spring or a helix. Right? No matter how you try to do it, there's no rotational axes, there's no mirror planes, there's no improper axes, there's nothing. Okay? It's possible to have a point group that has, in addition to identity, just a single mirror plane in the plane of the molecule. This is a nice example of that. You can see that there's a mirror plane in the plane of the molecule, but there's nothing else. There's no C2 axes of any sort. Nothing else. Okay. So we call this the CS point group. It's also possible to have just an inversion center. That's the CI point group. Here's an example of a molecule that just has an inversion center in addition to the trivial identity operation. So you can see if we invert here, the hydrogens exchange, the chlorines exchange, the fluorines exchange, and the carbons exchange. Game over. Right? But there's nothing else. There's no C3 axis here because if you did a C3, the hydrogen would then occupy the fluorine position, and that's not okay. There's no C2 perpendicular. Okay? There's nothing else. Does everybody see that there's no C2 perpendicular, like coming out of the board? Right? If you do the C2 operation, this chlorine is above the plane, that chlorine is below the plane, so you don't have an equivalent configuration. Okay? That's one way to see that. These are sometimes difficult to identify, but they're the simplest. Okay? Sometimes it's hard to take an object and convince yourself that there's no operations other than a single mirror plane, for example. On the other side, so those are the low symmetry point groups. On the other side, we have the high symmetry point groups. These are point groups that correspond to polyhedra, typically. Tetrahedra, octahedra, cubes, icosahedra, high symmetry objects. There are three main types of high symmetry point groups. tetrahedral, which is usually for the highest symmetry, is called TD, octahedral, OH, and icosahedral, IH. Okay. These point groups are derived from the Platonic solids. Okay. The solids described and captured the imagination by Plato. So the Platonic solids are listed down here. There are 5 regular Platonic solids: tetrahedron, octahedron, cube, dodecahedron, and icosahedron. And I've labeled their point groups next to them. Let's look at the 3 different main point groups here. The tetrahedral point group has all of these operations. There are 24 total operations in the complete set for the tetrahedral point group. Great example, of course, is methane, right? That's the most familiar example. What distinguishes tetrahedral symmetry is that you have 8 individual C3 operations. There are 4 C3 axes in the molecule down the carbon-hydrogen bond, each individual carbon-hydrogen bond. And there are 2 operations that correspond to each one of those axes. So if you have 8 different C3 operations and 4 different C3 axes, then you have tetrahedral symmetry. In addition to the C3s, you have C2s, which split the carbon-hydrogen-hydrogen bond angle. And as we described last time, you have S4 axes as well. Okay. Octahedral symmetry, here's SF6. This is an octahedron. 48 operations in the full octahedral symmetry point group. What's distinguishing here is that you have C4 axes and you have a ton of mirror planes in there. Okay, so if you have C4 axes and you have a bunch of perpendicular mirror planes, it's quite likely that you've got octahedral symmetry. That's the defining characteristic of an octahedron. Icosahedral has 120. That's the most symmetry operations for any point group. This is an example of an icosahedral symmetric object. This is Buckminster fullerene, which is carbon 60. 60 carbon atoms arranged in a cage that look like a soccer ball. Okay. You have pentagonal symmetry. So you can see this pentagon here. There's also hexagons in this particular object. But the characteristic feature of the symmetry is that you have C5 axes and you have a ton of them. Okay. 6 different C5 axes, I believe. And so, it would be brutal, and we're not going to list all of those different and visualize all those different operations, but there you have it. Okay? Those are the possibilities. There are several different kinds of tetrahedral, octahedral, and icosahedral point groups. Okay? There are actually 7 altogether. This is a table from a book describing all 7 different point groups. We have 2 different kinds of icosahedral, 2 different kinds of octahedral, and 3 different kinds of tetrahedral point groups. In addition to the 3 that I showed in the last slide, TD, OH, and IH, there are point groups that correspond to the same symmetry but without any mirror planes. So that's just called T, O, and I. So that's I, O, and T. And you can see in this list, here are all the mirror planes here. And for the O and the I and the T, there aren't any mirror planes present. They're just blank there. Okay. So it's the same symmetry, just without mirror planes. And it's possible to have molecules that have just O, I, or T symmetry. And finally, so that accounts for 6. And finally, the 7th one down here is called TH. And that's generated by taking the T point group and adding an inversion center. And then you get TH symmetry. And that rounds out all the possibilities, all the unique possibilities for point groups. I show down here because I was interested for a molecular example of TH symmetry. And this is the example here. This is hexapyridine iron, 2+. Right? So you have these pyridine units that are oriented like this. They're canted relative to one another. And so you don't have an octahedron here because there's no C4 axes. But what you do have is a C3 axis that's coming right out at you. Okay? There's a couple of others, right? There have to be 4. And you have an inversion center. You can see that if you invert this pyridine, it comes right down here. If you invert this pyridine through, it comes there, and so forth. So you can have tetrahedral symmetry with an inversion center, which is not the full tetrahedral symmetry of like methane, right? Remember, methane itself lacks an inversion center. Okay. So we have the 3 simple low symmetry point groups. We have 7 high symmetry point groups that you encounter fairly commonly in molecular chemistry. Let's look at the others. There's not that many more. Right? There are basically 4 more classes that we have to describe. One is pretty simple, linear point groups for linear molecules. There are 2 point groups for linear molecules. If you have a linear molecule that looks like this, it's not symmetric in this plane, what we have is a C infinity axis in this direction that contains all the atoms of the molecule. Rotation by any angle gives us a symmetry operation, gives us an identical or an equivalent configuration. Okay. So we label that as a C infinity axis. And this little Greek letter there tells you the angle is what is infinite. Okay. And in addition to that, of course, you also have an infinite number of mirror planes that run along the molecular axis, right? Infinite number with an infinite step size in the angle. We call that point group the C infinity V point group. Trivial to see it, right? If you have a linear molecule, it's going to be a linear point group. It's either the C infinity V or the D infinity H. Let's talk about the D infinity H. It's got the stuff that the C infinity V has, but in addition, it has an inversion center and or a mirror plane that bisects the molecule like that. And so we have inversion labeled there. We have the infinite number of vertical mirror planes, right, in this direction. We also have, in this case, S-axes. This is just because we have this mirror plane or this inversion center. So if the molecule is symmetric, when it's bisected and it's linear, then it's D infinity H. So all you really have to ask yourself when you encounter a linear example is it symmetric or is it not symmetric? That's the distinguishing characteristic. Okay. So low, high, linear. There are three more. We have the D, we have the C, and we have the S point groups. Let's look at the D point groups. The D point groups are those that have n number of perpendicular C2 axes perpendicular to a principal axis. Okay. So anytime we have perpendicular C2 axes for a molecule, it's going to be a D point group. The question then is just, what D point group are we talking about? We have Dn, we have Dnh, and we have Dnd. Those are the three possibilities. A Dn point group does not have any mirror planes. Okay. The complete set of symmetry operations depends on n. Okay. So let's say that n is 3, so we have a D3, for example, which is shown here. Then we're going to have the identity. We're going to have 2 C3 axes, and we're going to have 3 C2 axes. And that would give us the complete set of operations for a D3 point group. Notice there are no mirror planes, there are no inversion centers, etc., etc. Right? This is called a pure rotation group, because all you have is just simple rotations. Okay, and this is a nice example of D3. It basically looks like a propeller with 3 blades, and if you rotate the propeller by 120 degrees, you get the same guy back. You also have perpendicular C2 axes here, which is why it's a D point group and not something else. So here's one of the 3 perpendicular C2 axes. All right, let's say now that we have a flat molecule like this, BF3. Okay. We're obviously going to have now mirror planes that are going to pop up. So we have, in this particular case, a horizontal mirror plane, a mirror plane in the plane of the board that's perpendicular to the principal axis, which is coming out at you, C3 axis. Okay. So the number of symmetry operations is, again, going to depend on n, and this is how the order relates to n. The order is equal to 4 times the number of symmetry operations. Or sorry, 4 times the order of the principal axis. This molecule here has a C3. It has a perpendicular mirror plane. It has 3 perpendicular C2 axes in those 3 directions there. It has vertical mirror planes, like there. This is a so-called D3H point group. And this is the full list of symmetry operations that correspond to this particular D3H point group. So the differentiation between the N and the NH is that we have a horizontal mirror plane and a bunch of other mirror planes popping up as a result. Okay? And then finally, we have the D and D. Again, the order is the same as it is for the DNH. Here's an example of a D2D point group. This is allene. Here we have these 2 hydrogens in the plane and these 2 hydrogens perpendicular, 90 degrees, coming out and in the plane. Right? And you can see what we've got here. We have a C2 axis, right? You can go along this direction here for the C2 axis. There are perpendicular C2 axes as well. They are located 45 degrees between this plane and this plane coming out at you. Okay. So if you have one axis 45 degrees coming down and coming out of the board, and another axis 45 degrees going from down into the board in that direction, those are your two perpendicular C2 axes that have to be there if it's going to be a D point group. In addition, we can count up all the other things that would be in this point group. You're going to have an S4 axis and other things. This is D2D with all of those symmetry operations present. Okay, so of course, we can have a D3D, we can have a D4D, we can have a D5D, et cetera, et cetera. They're all going to have a different number of symmetry operations, but in general, they're going to look fairly similar in terms of having mirror planes present, having horizontal mirror plane for DNH, not for DND, et cetera. Okay. So we have the D point groups. The last two are the C point groups and the S point groups. The C point groups are almost exactly the same, except they don't have perpendicular C2 axes. Okay, so here are the C point groups. These point groups have a principal axis CN, but no perpendicular C2. So that's the distinguishing characteristic differentiating D and C point groups is the presence of perpendicular C2 axes. Just like before, we had a DN, now we have a CN, we have a CNV now, and we have a CNH. No mirror planes. Here's an example of a C2 molecule here. Okay. Rotational axis coming right out at you. CNV, we have vertical mirror planes. In this case, NH3, we have a threefold axis running this direction. The molecule is not planar, so we don't have a horizontal mirror plane, but we do have vertical mirror planes. We have three of them. Okay. Going through the nitrogen and one of the hydrogens, this nitrogen and that hydrogen, this one and that one. Those are the three different mirror planes. Okay. Vertical, so they contain the axis of the principal axis of the molecule. This is an example of C3V point group. And there's 6 total operations for that particular point group. So CNV is when we have vertical mirror planes. CNH is when we have horizontal mirror plane present. So an example of that is this molecule here. This is in particular C2H. It has a twofold rotational axis coming out at you. And you can see, of course, that it has a horizontal mirror plane in the plane of the molecule. Okay. So C2H gives you identity, the C2, the inversion. You can see inversion center and the horizontal mirror plane. That's the complete set of operations for this molecule. Okay. And there's only one more kind of point group, and that is the S point groups. So the S point group is as follows. Yeah, Glenn.
Where's the C2 axis in that?
On this one here?
Yeah.
Coming right out at you.
Oh.
So if you rotate 180 degrees, the hydrogens interchange, the chlorines are on the same side, and the fluorines are on the same side of the molecule. Yep. Other questions about this so far? I'm kind of moving quickly through this. So, and it's going to take, depending on your ability to visualize three-dimensional space, it's going to take some time to become familiar with these operations and comfortable with them. The final point group are the S point groups, and there's only one kind. It's typically labeled as S2N. If an object has a principal axis and it has an S2N axis parallel to that principal axis, but it has no perpendicular C2s and no mirror planes at all, then it's going to be an S2N point group. These are much rarer than a lot of the other point groups, so we won't encounter this, maybe not at all, other than this example. Okay, we'll see. So here's an S4 example. This is tetracobalt, this is CP, right, cyclopentadienyl. So there are 4 cyclopentadienyl rings and a cluster of 4 cobalts. Here's the cobalt 4 cluster here. Now this is kind of a difficult one to visualize, but there's a C2 axis coming out at you right there that goes right through the middle of those bonds. Okay. If you rotate 180 degrees around that, that drives this cyclopentadienyl around and puts it here with the same orientation. You can see this is slightly skewed, right, out of the plane. This is slightly skewed in the appropriate way. And these two, which are pointed into the plane, also rotate around and adopt an equivalent configuration after a C2. But there are no mirror planes in the molecule, and that's because these cyclopentadienal rings are slightly canted relative to one another. And so there is no mirror plane, say, along this line here, because that would move this atom slightly across the mirror plane to that position, and there's no atom there. Okay? But there is an S4 axis. Right? So it's parallel, to the C2. If we do an S4 operation, we rotate this guy 90 degrees. It would occupy that position in the plane, and then we would do a reflection perpendicular to the plane, and it would pop it out into this position. And the same thing for the other three CP rings, and the same thing, of course, for the cobalts. So we have, in this case, for an S4, just 4 symmetry operations. Identity S4 C2, which is the same thing as doing the S4 twice, right? Just in different clothes, and the S4 cubed. Okay. You can find S4s, S6s, S8s. It's very rare to see anything else in molecular symmetry. Okay. It's possible, but very rare. Okay. How do we tell when we're given a molecule just on a piece of paper what its point group is? Well, lucky for us all, there is a tried and true, fail-safe decision tree that we can follow to categorize point groups. This is the decision tree, page 81 in your book, figure 4.7. It works every time. What we do is we start here at the top of the decision tree and we make our way down, and you can see there's a split or two that happen. First question we ask, is it a group of low symmetry? If it is, then it's either the C1, the CS, or the CI, and we're done. If it's not, we go to second step here. Is it a group of high symmetry? Yes or no? If it's not, then we ask the question, what is the highest order axis we can find? What is the principal axis of the molecule? And this sets us up for proper determination of the point group. Is there a C2 only? Is there a C3? Is there a C5? Okay, we identify what that principal axis is. The next step is then to distinguish between D groups and C or S groups. Are there perpendicular C2 axes in the molecule? If there are, then we go to the D decision tree, right, the branch. If there are not, we go to C and S branch. Okay. Let's say that there are perpendicular C2 axes, so we know we have a D point group. Then the question is it D, I can't read this, NH, ND, or DN? Those are the 3 different types, right? So the decision then comes down to, is there a perpendicular mirror plane, a horizontal mirror plane? If yes, it's DNH. If not, go down here. Are there parallel mirror planes, parallel to the principal axis? If yes, it's DND. If not, it's just DN with no mirror planes at all. And that's the end of that part of the decision tree. We've got basically the same set of decisions here. Okay? So if there are no perpendicular C2 axes, it's either C or S. We ask ourselves next, is there an H mirror plane? If there is, it's CNH. If not, we come down here. Are there vertical mirror planes? If yes, it's CNV. If not, we come down here. Is there an S2N axis? If yes, it's S2N. If no, it's CN with no mirror planes at all. Okay. And so you play this little game here, and typically you want to, for a lot of molecules, it ends up practically being these questions here. Okay? Identify the principal axis, and then find out if there are perpendicular C2 axes, and that sets the stage for all the rest of it. So perpendicular C2 axes, horizontal mirror plane, vertical mirror plane, and then you're done. Okay? So let's look at a couple of examples in the last 5 minutes. Phosphorus pentafluoride is a nice example. Is it low symmetry? No. Is it linear? No. Is it high symmetry? By high symmetry, I mean, is it tetrahedral? Is it octahedral? Is it icosahedral? It is not, right? So tetrahedron has 4 triangular faces. This one doesn't. This has more. Right? So it's not low, it's not high, so we come to the decision, what is the principal axis of the molecule? So what is the principal axis of this molecule? C3, right? There's a C3 axis, fluorine, phosphorus, fluorine, right there, right? Rotate 120 degrees around that, and you're going to interchange these fluorines in the plane. Okay? So we have a C3 axis. The next question, are there perpendicular C2 axes? And there have to be either 0 or 3 of them, we know, right? There are perpendicular C2s, right? There they are. So they go from phosphorus to fluorine, each of the three individual fluorines. Rotate 180 degrees around that axis, and you flip these fluorines up there, right? And you flip the other two fluorines in their place as well. Okay, so what does it mean now if we have a C3 and we have three perpendicular C2s? What is our point group? We're in the D branch of the decision tree, right? So the next question is there a horizontal mirror plane? And remember, horizontal always means perpendicular to the principal axis. Okay? Click, click, click. Yes, there. There's our horizontal mirror plane, right? It's in the phosphorus 3-fluorine plane. It's a mirror plane that just would keep all the four atoms that are in the plane the same and would drive these fluorines into one another. Okay? And so, yeah, we've now finished. We've determined that there's a horizontal mirror plane. We have perpendicular C2s, and we have a C3 principal axis. So that means that we're D3H. Okay? That completes the decision tree. In this case, there's not that many decisions because we found that we have a horizontal mirror plane. D3H, you could build up all of the different symmetry operations. What we'll show later is that there's a table at the back of your book that has all of these conveniently specified for you in the character tables in the back of your book. I think it's Appendix A or C or something. So there's a list of all of the different character tables that one would encounter. And D3H is one of them. Okay, so phosphorus pentafluoride is D3H. It has D3H symmetry. It's in the D3H point group. Let's look at diborane. A cute little molecule. Okay, we've got these hydrogens 90 degrees, and we've got these hydrogens in the plane. Right? So there's two planes to this molecule. Is it low? Is it high symmetry? Or is it linear? No, no, no. Right? So let's find the principal axis. What is it? Is there a C4 axis in this molecule? You hope so? A big fan of C4 symmetry. There's only C2 in this one. Right? So there's one of the C2 axes. There's a couple perpendicular C2 axes. We chose this one. Doesn't really matter which one you choose, but we chose this one because it contains the boron-boron bond. Okay? But you can see that there's also a C2 that goes out of the plane and a C2 that goes up and down like this. Right? So what does that tell you right away? If there are two perpendicular C2 axes, we're again in the D point group selection tree. And it's either D2, D2H, or D2D. We have to ask ourselves about the horizontal mirror plane. There is a horizontal mirror plane, right? That's perpendicular to the principal axis that we selected at the beginning between the borons. And so that, again, drives us to the D2H point group for this molecule. Sorry that this one and the previous example were kind of similar. Kind of boring. One last example, and then we'll finish up. Let's look at this one. This is a famous molecule, 18 crown 6 ether. It's called crown ether because it looks like a crown that you could put on your head. This is the full ridiculous organic chemistry name to it. Right? But this is why everybody calls it 18 crown 6. There are 6 oxygens and there are 18 carbons. That's why, or 18 total molecules in the ring, or total atoms in the ring. So it's 18 crown 6. Is it high symmetry? Is it low symmetry? No. Right? No? According to my slide, anyway. Find the principal axis. What's the principal axis? There's a C6 right there. Right? Here's the symbol for the C6 is a little red hexagon here, right in the middle of the molecule. You rotate 60 degrees and you interchange all the atoms. Okay. Does it have perpendicular C2s? It does not, right? And that's because the oxygens are high and the carbons are low, right? You can't get a perpendicular C2. So that's what you would try to do to draw it, but in fact it doesn't have one. If we had a C2 axis, that would rotate the oxygens down underneath that axis and doesn't work out. So we know we're not D. We know that we're either C or S, right? Is there a horizontal mirror plane? So there's no horizontal mirror plane that's perpendicular to the C6 axis. There are, however, other mirror planes in the molecule. There are vertical mirror planes and dihedral mirror planes. vertical mirror planes passing through the atoms and dihedrals passing between the atoms. Okay? And so what do we have then? We have a C6V point group here. And we ruled out the H, we ruled out the D, but we have parallel vertical mirror planes, C6V in this case. Practice assigning point groups, and I'll see you on Wednesday.